Hello, this is Sarah Pessognelli. I'm going to be talking about my project predicting FEMA costs, weather data, and AI/ML. The goal of this project, we want to visualize areas of the U.S. most affected by severe weather, determine what severe weather incidents are increasing in frequency, build some AI/ML models to make predictions about the cost of those disasters, and just, in general, get a better understanding of how to allocate federal FEMA funding. The dataset is the Open FEMA dataset is a comprehensive list of all FEMA-funded disaster relief projects since 1998 and includes metadata about those projects like the incident type, the date, and importantly, how those funds are allocated. We also need the FCC state to county FIPS codes, which is just a comprehensive list of all the US state and county names to a unique FIPS identifier. We're also going to use the Python packages CPI, which is an inflation calculator, and Meteostat, which is a local weather data API. The initial observations, this is a huge data set. There's almost 800,000 entries in 24 variables. A lot of these variables are just unique identifiers that we don't necessarily need or redundant information. So we have the county code, the FIPS code, and the county name, and the same for the states. So a lot of this can be pared down in our data cleaning. So first thing we're going to do is take a simple random sample. Of our 800,000, we're going to, just for the sake of this analysis, drop down to 1,000. We're going to use our create a FIPS dictionary, which maps the county and state name to the unique FIPS identifier. That'll make it easier to get information like the lat and lon. We're going to remove some NaN values, and we're going to do some feature engineering, mostly adding features or adjusting existing features. So that's what that feature engineering looks like. And here is our exploratory data analysis. So first thing I looked at was some histograms just to get an idea of the spread of our data. These were ones I thought were interesting. So you can see there's some pretty wide spreads in our temperatures and precipitation. Kind of makes sense. There's a lot of different types of disasters included in this data set. The project amount is interesting too. You can see that most are relatively inexpensive. I should note that it's cut off, but this is a 10 to the 6th. So you can see that most are not quite $1 million, but you have a few that are almost $2 million. And then the lat and lon I thought was interesting because you see some spikes in the lat and the lon, which makes me think maybe we have some hot spots for certain disasters. I also made some box plots, which are very good at displaying outlier data, but because of the nature of this data, we're talking about extreme weather, we probably want the extreme values. So I opted not to remove any outliers from this data. The correlation matrix was pretty interesting. There's some pretty strong correlation between the different weather data that we added and then imputed. And they seem to be correlated pretty strongly with each other, which is interesting. And they are also pretty highly correlated with the costs, which is promising. Made some pair plots too. They were interesting. You can see this red cluster here is hurricanes, and you can see that the average temperature is pretty high. Makes sense. They tend to happen in the summer. And the wind speed vary a lot, which also kind of makes sense depending on where you end up in that hurricane. And versus severe storms, which have lower, a wider spread of temperature and also lower wind speeds. That's that big smudge of blue dots. So for feature encoding, we found our nominal features, which are features that don't have a natural direction to them, or things that repeat a lot, like your month and your season or your county or state. And we are going to simply one-hot encode them, which is just add a dummy variable for each possibility. We also identified our ordinal features, which are ones that are categorical but do have a natural order to them. So things like project size or the process step, project status, year, things like that. So once all the categorical variables are handled, we move on to actually creating our data sets. So we made 4. We made dataset 0, which is just using the z-score scalar on the continuous variables to standardize them. Then we do principal component analysis on just the continuous features to try and reduce the number of features. 2, we apply PCA to the encoded categorical variables, which are now integers. And then for our last one, we create a new response variable that just bins the project amount into categories based on the quartiles and apply a k-fold cross-validation. So here's our regression model analysis. Linear regression, decision tree, random forest, gradient boost, SVM, XGBoost. And here is our results. Believe it or not, those are R-squared values, so they all perform terribly. That was the impetus for moving on to a classification problem instead. The first thing I did was check for class imbalance, which there was. You can see that most of the projects are below the project mean and only some are above. So I went ahead and fixed that using SMOTE-NC. Then the classification models that we used included logistic regression, decision trees, random forest, gradient boost, SVM, KNN, and XGBoost. Whew, all right, that's a lot, but they performed pretty well. You can see that we're pretty much in the low 80s to low 90s, with the exception of SVM, which is essentially a coin toss, but overall, pretty good accuracy. Then I performed a grid search to see if I could improve those numbers at all. A grid search is pretty simple. You're just creating a grid of different hyperparameters that you're going to search through for each type of model to find the best set of parameters to use. Here's an example for the random forest and XGBoost. And this was definitely worth my time. It improved them a lot. You can see we're now pretty much sitting in the high 80s to mid 90s. I think the most notable success story here is SVM. If you remember before, it was basically just a coin toss, and now we're up to a 93% accuracy. So that's pretty substantial, and I think it just goes to show how these parameters can, model parameters can really change the outcomes of your models and why a grid search might be worth your time. The next thing I did, once I made a predictive model that could tell us about the price, was look at the frequencies. I use Sarima for this. It's a seasonal ARIMA. So essentially what it's doing is looking at trends that are seasonal. So hurricanes would be a good example of that because there is a hurricane season. So you can see the natural seasonal nature of these hurricanes with our frequency chart here in blue. This is the historic data. And then here at the end, you can see the forecasted data from Sarima for the next 2 hurricane seasons, 2026 and 2027. So it looks like we're going to have something like 5 significant hurricane disasters that need FEMA funding. The last thing I did was some clustering, excuse me, of that hurricane data. Quick elbow chart. Show that 4 clusters was going to be a good number for us. And you can also see that the results of this kind of make sense. We have one centered almost right on New Orleans, which makes sense for this area of the Gulf and historical events like Hurricane Katrina or Hurricane Harvey in Galveston. Central Florida, of course, makes sense. Both sides of the Panhandle get annihilated by hurricanes pretty regularly. You have yellow is centered on mid-North Carolina, which Hurricane Harvey last year proved is accurate. And you also have, this is just north of New York City, so things like Hurricane Sandy accounting for that. So we went over a lot of my conclusions, but I'll talk a little bit more about the future work. I would like to focus a little bit more on the clustering aspect of this. I think that there's more to be done there. dbScan would be an interesting algorithm to use. It scales based on density. I also think it would be interesting to weight each point in our k-means clustering by how much they cost. because that would definitely move our centers a little bit and would hopefully move them towards areas even more prone within those clusters, more susceptible to more expensive damage. I would also like to revisit the predictive models a little bit. Maybe take another stab at regression, see if that could work at all, or make a more informative classification model, more bins, to more ranges of narrower ranges of dollar amounts that would be more informative at making predictions on how much specific areas could expect to spend each year on disaster relief. Thank you for listening to my presentation. I hope it was informative. There's a lot more information in my final report. Thank you. Goodbye.